Hey, welcome back. And this lecture is on binary search trees, as you can see from the slide. This is the last lecture that the exam involves. And so lecture 16 is going to begin AVL trees, which will build off the lecture you're about to hear, but it won't be on the exam. And so these first 15 lectures are what the exam involves. And so anyway, that said, the binary search tree is our motivation to improve search time. Up to this time, the only time we didn't have linear time search was if it wasn't really a search at all. If we had an array and we knew the index where our element was located at, we could use that index to jump to the element cell in constant time. Otherwise, if there was an actual search or a find involved, then it would be linear time, either searching the array or the linked list. We didn't really search on stacks or queues. We could only look at the first element. And then for trees, as we've seen them so far, it's necessary to search the entire tree all over the place to look for the value. So you have to do a traversal, and then each node say, is this what I want? Is this what I want? Until you either find it or you search the whole tree without having found it. Binary search trees are based on a very helpful observation, which is that if we have a node, we have our left and our right pointers, and we can make use of a very useful principle here, which is that if we have a value x in the node, then we could put things here less than x and put things here if they're greater than x. That is, as we construct the tree, as we insert nodes into the tree, we can follow a rule that says the fact that we have two pointers divides the space of all non-x nodes into two parts. Whatever is in the subtree, x is the root of the tree. Whatever is in this tree relates to x in one of two ways. Either it's less than x or it's greater than x. And you say, well, what if it's equal to x? The answer is we're not going to worry about that. We could certainly say, okay, put everything less than or equal to x here, put everything greater than x there. We're not, in general, and I may have mentioned this in an earlier lecture as well, in general, for the things we discuss, dealing with the duplicate element is simply going to be a small tweak of the basic idea. So as we deal with this idea today, we're going to assume no duplicate elements. From time to time, I'll mention, okay, here's where you would deal with duplicates if you wanted to, but the way in which you can deal with them is up to you. And here, right away, we have two options. I could put duplicates in the left subtree or in the right subtree. The idea being that I'm not going to worry about describing what would happen if we wanted to use duplicates. There's a number of different things we might do. They're all just going to be small tweaks of the basic idea. So let's focus on the basic idea, which is all the elements being distinct, and then if you want to deal with duplicates, you can mess around with how you'd handle them yourself. So the idea here is that this isn't quite as useful if this applies only to a particular node, but the idea is for a binary search tree, what it has is an ordering principle, which is the idea that at every node, items in that node's left subtree are less than that node's element. And those in right subtree are greater. That's the ordering principle here, so let me go ahead and underline this. And basically, that's what I've drawn here, except this is not just at the start of the node. This is at every single node in the tree this applies. For if you have some value x in the node, things to the left are less, things to the right are greater. And that's the ordering principle that makes a binary search tree work, because given that then, being able to deal with searching this tree is going to be a lot more helpful to us. The reason we had to search the entire tree before is because we had no idea where things would be. In that last lecture, if we're looking for the element q, we don't know to start with whether q is in the left or right subtree, and so we have to search them both. And if we decide to search the left subtree first and we don't find Q, we still have to search the right subtree. And if we are looking for something and decided to search the right subtree first and it wasn't there, we'd have to look at the left subtree. There's no way to get around it. In order to verify an element isn't there, we have to search both subtrees because it could be in either one. However, if you have this applying at every single node, that the node's left subtree has those items are less than the node's element and the right subtree elements are greater than that node's element, you end up with a tree like this. And this is just coming up with some random tree off the top of my head, but you have here, say, a root pointer, as always, to the node 8. And let's say we have here 3, and we have here 1, and 5, and 4. Let's say we have here 20. Here we have 18, 14, 28, 24, 32. Again, just completely random example off the top of my head. The idea here is this is a height 3 tree. Level 8 is depth 0, or node 8 is depth 0, 3 and 20 are depth 1, 1, 5, 8, and 28 are depth 2, 4, 14, 24, and 32 are depth 3. In retrospect, I wish this would have been a little bit lower, but that's 4. That's how it goes. That way it lines up better, all those together. So we have here the idea then, notice that from 3, 1 is less than 3, 5 and 4 are greater than 3. At 5, 4 is less than 5. There's nothing here in 5's right subtree, so that's a moot point. 1, 3, 4, and 5 are all less than 8. 14 through 32, all these nodes are greater than 8. 14 and 18 are less than 20. 14 is less than 18. 24 is less than 28. 32 is greater, and so on. The way these are arranged follows that ordering principle. Everything at any given node, pick any node in the tree, everything to its left is less, everything to its right is greater. And of course, there are nodes that aren't in the left or right subtree. So for example, for 18, it has one node in its left subtree, no nodes in its right subtree, and then a bunch of other nodes that aren't part of 18's tree at all. So we're talking about here just the subtree rooted at 18. Dealing with such a tree, we have then one interesting thing you might note is the in-order traversal for such a tree is guaranteed to print out the values in lexicographical order. Whether, numerical order if you're dealing with numbers, alphabetical order if you're dealing with characters or strings, whatever ordering you've defined in your elements, the elements from low to high in order will be printed using an in-order traversal. The reason being that if everything in the left subtree is less than your node, well, an in-order traversal will print everything in the left subtree before your node itself, and everything in the right subtree will come after your node. So your node will come between everything that's less than it and everything that's greater than it in its subtree. And if we do that for every tree, basically we say, well, everything here will be printed, which is less than 8, and then 8, and everything here, which is greater than 8. And we look at this detail, all the things greater than 8, what order do they get printed in? Well, the stuff less than 20, and then 20, and then the stuff greater than 20. So, and so on and so forth. So as a result, if you take that down to the lowest levels of the tree, the idea is that every single subtree you print will be printed in order of the lower than the root elements, and then the root element, and then the greater than root elements. And that fits into a larger pattern of, well, now those are less than or greater than some other root, and some larger tree. So an in-order traversal on a binary search tree will print out the values in lexicographical order, which is kind of neat. It's one property you should remember. But what's neater is the ability to do a search here. Because note, if I'm going to search this tree, I can take advantage of the structure to limit myself to exactly one search path from top to bottom. That is, if I want to, for example, search for 5, I say, well, 5 is less than 8. So firstly, 5 is not equal to 8, so I haven't found it. Since 5 is less than 8, I must look at the left subtree. 5 is greater than 3. It's not equal to, so it's not at that node, so I must search on the right subtree. And now I say, hey, 5 is equal to 5, I found my value. And you think, so what? Well, here's the interesting thing. Same thing with 14, by the way. So let's pick out 14. 14 isn't in this node, and in fact is greater than 8, so I move down here. to the right because greater means go to the right. 14 is greater than 20. It's not equal, so I haven't found the value, but it is greater. I'm sorry, less than. Pardon me, 14 is less than 20. So I move to the left. Less than means the left. 14 is not equal to what's there, and in fact 14 is less than what's there, so I again move to the left, and now lo and behold I found 14. Double equal. Let's look at what happens now if I'm looking for something that isn't there. For example, 23. Well, I say, searching here, well, hold on, let me point something out here first. The idea at each of these was the ordering principle directs me into a particular subtree. So when I'm looking at 8, I say, well, I know 14 isn't here. Now, in the other kind of trees, the ones that were not binary search trees, that were ordinary binary trees, like the ones we looked at in the traversal lecture, I would have had to now search exhaustively both of those subtrees with the hope I would find 5. Here I said, I know 5 can't be in this subtree, in the right one. 5 is less than 8. So if 5 is anywhere at all in this tree, 5 would be in the left subtree of 8, not in the right subtree of 8. So I search only the left subtree, and that's what tells me to search down in this direction, to search on the left-hand side of 8. Likewise, when looking for 14, I know 14 can only be in the right subtree of 8. It couldn't be in the left subtree of 8 because 14 is greater than 8, so it wouldn't be in the left. So if I'm going to now search for a particular value that is not there, for example, 23, well, I say this 23 is not equal to what's in this node, but 23 is greater than what's in that node, so I look to the right. And I compare it to here, and 23 is not equal to that, but 23 is greater than what's there, so I go to the right. And 23 is not equal to that, but 23 is less than what's there, so I go to the left. And 23 is not equal to this, but in fact it's less, so I move to the left, and well, lo and behold, we have a null pointer here that we typically don't draw. I hit a null, and I say, whoops, I hit a null. And whenever I hit a null, that means I have not found my value. 23 was greater than 8. 23 was greater than 20. It was less than 28. It was less than 24. And then we hit a null. And what that means is there's nothing to search for in this subtree. I have said, and this, because of the slide we're using, I think here is why I'm using this overhead slide over these, and that's why that ending is not showing up too well. So let me move this here for the moment. We said, this is my worry, that these overheads would reflect, but hopefully it won't be too bad. The idea here, the concept is that we are searching trees for a value. And I'm saying here, when I look for 23, it could potentially be anywhere in this tree. But then once I read the root node, I know I only have to search the right subtree. So we talk about moving to the right. What we're really doing is saying, what subtree should I search? It's either, if it's going to be in the tree, it's either in the root or it's in one of the two subtrees. And I compare first with the root, and I say, well, 23 is not equal to 8, so I haven't found this. Therefore, if it's anywhere, it's going to be in one of the two subtrees. And when a binary search tree lets us do, the power of a binary search tree is it says, I don't need to search both subtrees, I only need to search one of them. Since 23 is greater than 8, I don't need to search the left subtree, I just need to search the right one. So I search the entire right subtree, all those nodes. But what that means is I read the first node, and since it's not the root, it has to be either in the left or right subtree, and I know it's in the right subtree if it's anywhere because 23 is greater than 20. It wouldn't be in the left subtree of 20 because it's not less than 20. So now it's to the 28 rooted, the subtree rooted at 28 that I search. And I say, well, since I'm not equal to 28 and I'm less than 28, I search its left subtree. So it's the subtree rooted at 24 that I then search. And 23 is not equal to 24, and in fact is less than 24. So I search its left subtree. And so the idea is when we narrow a subtree, we're narrowing further and further. We're saying, okay, it's not everything, it's the stuff greater than 8. Oh, okay, it's the stuff greater than 8 and also greater than 20. Oh, it's in the subtree of elements greater than 8, greater than 20, but less than 28, and that's these. And now we're saying it's in this collection of elements greater than 8, greater than 20, less than 28, and less than 24, and that's narrowed our collection of possible elements down to nothing. And that's basically, you can picture the tree being arranged like that, where these decisions are narrowing the process down. We have a span of everything in the tree, and then we say, Well, it's the stuff that's greater than 8. Oh, and also the stuff greater than 20. But it's not quite so big that it's greater than 28. In fact, it's between 20 and 28. In fact, it's between 20 and 24. And now that narrows our selection of elements down to absolutely nothing. And since the selection of elements is narrowed down to absolutely nothing, that means our value is not in the tree. It's the only place 23 could be. 23 could not have been in the left subtree of 8. 23 could not have been in the left subtree of 20, or the right subtree of 28, or the right subtree of 24. So if 23 was not any of the nodes we've looked at already, then it has to be in the left subtree of 24. And since that subtree is null, that means 23 is not in this tree. And we've accomplished that by looking at only 4 nodes, and I guess reading that fact that this is a null pointer as well, even though we have 11 nodes in the tree overall. And so since we have 11 nodes in the tree and we've only looked at 4, that's a pretty cool thing. It's pretty powerful, because the other searches would have required looking at all 11 nodes. The searches based off our traversals would have required looking at all 11 nodes before recognizing that 23 is not in the tree. Now we can look at only 4 nodes and a null pointer and recognize that 23 is not in the tree. And as trees get larger and larger, this becomes more and more help. Imagine a 1,000,000 element tree where you look at 20 nodes and you recognize, oh, 23 is not here. Instead of searching 1,000,000 nodes, you search only 20 potentially. That's very, very helpful. And so what binary search trees will do is lessen the time it takes to search for things, because it's arranged the tree so that we only have to look at one particular path rather than the entire tree. The consequence of this, though, is that we have very specific insert and remove procedures we need to follow, whereas in the sort of more ordinary trees we looked at last time, we could have dumped anything anywhere we wanted. If I wanted to make, X a left subtree of Z, hey, knock yourself out. Here, we have very specific rules as far as how we insert and remove, and we'll be looking at those today as well. So, what we need to do now is first talk about how we would write the find code. And so I'm going to write the same tree over again, but a little bit smaller so I have room to start talking about code. So this will be on your slide as well. So if you can't quite make out the numbers, you can at least make out the structure of the tree. Again, a concession to the very small amount of room I've got on this piece of paper compared to 4 whiteboards, which is what I normally write across in the regular lecture. 5, 18, 28, and then here I have 4, and here I have 14, and here I have 24, and 32. So there's my binary search tree. Now, dealing with the code that we want to look at, typically there are 4 cases we have to deal with. And so again, I'm not going to worry terribly about scoping this to a particular class. It's part of a tree class of some kind. We're dealing here with, this would be returning, int. We could return Boolean, but since, again, Boolean is not always supported by compilers because it's relatively a new addition to the C++ language. So we return an int, and it's 1 if we find the value and 0 if we don't. So given that, what we're going to pass in here is a node pointer tn and a whatever is held by the tree key. So we hold integers, we're looking for an integer key, E-type key, and I'm not quite sure, well, it'll be visible on your slide if it's run off the end there. It looks okay from my point of view. So a tree node tn, a tree node pointer tn, and an E-type key, and just as with the traversals, we would perhaps have a public version we'd simply call find, passing in the key, and then the implementation of that would be to pass in the key to a second version of find that also takes root as its first argument. And so that would be how this would work. We talked about that with preorder last time, and the same thing would be the case here. So typically we have 4 cases, and the first case we have to worry about would be if nothing is there. Say if I pass in a null pointer, what does that mean? And we've talked about that already on the previous slide. Or you can imagine if root points to null, what does that mean immediately? It means we haven't found our value. If the root, we're passing in the root of the subtree we want to, or sorry, we're passing in the pointer to the root of the subtree we want to search. And if the pointer we're passing in is null, that means the subtree we want to search is empty. If I pass in a null root pointer, the entire tree is empty. Or if I'm down to this 14, as it was last time, and I'm searching 14, then the entire left subtree of 14, or sorry, it was 24 last time. If I'm searching the left subtree of 24, well, that's empty. And if that pointer is null, and which it is here, the left subtree of 24 is null, and so if I'm going to search that subtree, I should immediately return 0. I know my search will be unsuccessful because it cannot be in a tree that has nothing in it, because nothing would be found in that tree that has nothing in it. Otherwise, the other possibility where there's 3 of them, we know Tn exists. So the first possibility, the one we really should check first, is that the key, is the key inside its node, because that's what we're trying to find out first and foremost. I've established the tree isn't empty, so then the question is, well, is the key inside its node? And if it is, so for example, if I pass in the root pointer and I say, I'm looking for 8, and we say, well, lo and behold, the element inside the root node is 8. We're done. We return 1. Yes, I found it. A more sophisticated example might return the pointer to the node itself so we can extract something from it, but for now we'll just return 0 or 1. False or true, yes, no, we found it, or no, we didn't find it, or yes, we did. And so, if I pass in a pointer to 24 and I say I'm looking for 24, have I found it? Well, lo and behold, that pointer's element is 24, so yes, we have. So in general, if we have a pointer to the node that contains the value we're looking for, then we return 1. There's 2 other possibilities. Both of them say that the value we're looking for, the pointer we send in is not null, so we do point to a node, but that node does not contain what we're looking for. Well, then the only 2 possibilities are what we're looking for is less than that value or greater than that value. And so I can say, I should have had an if here. It appears in your slide, but I didn't write it here, so there's an if. Otherwise, if, and here's the third case to worry about, if our key is less than what's inside the element, then that means we search the left-hand side. So for example, when I said I'm looking for 5, 5 is less than 8, so I search the left-hand side of 8, or the left subtree of 8. And so what I need to do here is call find on Tn arrow left and pass in the key. So those are my 2 arguments. I'm going to write something here, which is why I've left a blank space, but we'll get to that in a moment. So I would then say, well, I'm calling find. The arguments I pass in are Tn arrow left and the key. And so, and the recursive call, that I'm making a recursive call to find. If I'm searching for 5, for example, then here I would say, well, I'm looking for 5. Since the root pointer is not null and yet 8 is not equal to 5, and 5 is less than 8, then I hit the third case and I say, I should call find looking for 5 on this pointer here, the pointer that is 8's left subtree. And so I would enter a second call to find in which this pointer would be Tn, the pointer to 3, and I'd be searching this subtree then for 5. And I would return 1 or 0 accordingly. So it's just like the discussion of pre-order where I have a second call to find, and a third call to find, and a fourth call to find, and however deep I need to go in the tree, I have this is my first, second, third, fourth, fifth, sixth, seventh call, however deep I need to go. They all have their own version of Tn. They're just different Tn's in different stack frames. So that same discussion with, if you're still shaky on recursion, that same discussion we had for pre-order works here as well. Now, one thing we might notice is, okay, I find 5, for example. I say I need to call find again on the left pointer of 8, and then since 5 is greater than 3, I need to call find on the right pointer of 3, which is what we'll do next. We'll say if the node exists, but we are not equal to the node or less, then we must be greater. And I don't even need to put an if there. That's the only other possibility, so I can put a comment there, that this has to be the case if none of the other 3 are true. Then I can say call find, passing in the right pointer and key. So if I'm looking for 5, I would say, well, 5 is less than 8, so I pass in the left pointer of 8. and now I'm pointing to 3, and then that second recursive call, Tn points to 3, and I say, well, Tn's not null, but the element 3 is not equal to my key, and yet 5, what I'm looking for, is not less than the element, which is 3. Since 5 is not less than 3, then it must be greater, and so that means I search down here on Tn, which is 3's right pointer, and pass in 5. So my third recursive call would have this pointer as Tn, and I would say I'm searching the subtree pointed to by this pointer for 5, and then my second case would trigger, and I'd say, well, return 1, because you found 5. And I return 1 back to the second recursive call, and it sort of sits there. We had no return value. Since find is expecting to return a value, you have to return something, and this is a very common mistake, very easy for you to miss. You need to say return here. You're calling find, but since this recursive call will return a value to you, you likewise need to send that value even higher. So the idea here will be that when you return 1 from the third call to 5, you then say, well, when you were in the second call and you made the third recursive call passing in this pointer and 5 as arguments, now the result of that recursive call is 1, and you send that back up to here. And now when you were in the first recursive call, making the second recursive call, passing in this pointer and 5 as arguments, the result of that second call is 1, and you pass it outward. And then the result of the first call is 1, and there you go. So you're saying, from the first call, which has the root pointer, you pass in this pointer, and there's your second call. This pointer is Tn in your third call. You return 1 to here, return 1 to here, return 1 outward. So as you return from the third and second and the first calls of find, you're passing this 1 up along that sort of chain of things until you finally return for good. And so that's how this would work. The 4 key ideas here are, the key ideas, you have 4 cases. Tn is either null, or your value matches what's in the element, or your value is less than what's in the element, or your value is greater than what's in the element. Those are your 4 cases. And when we start looking at insert and remove, those will likewise be the 4 cases we worry about. So, that said, we're going to save running time discussion for the very end of the lecture because it's going to be the same discussion for all 3 of them. Let's consider what happens when we insert. So let's go back to our larger picture of this tree that we can put slides on. And when we talk about this, we're saying, well, let's say I want to insert 23 now. Again, if there's bright spots, that's this odd reflection off these slides, these transparencies, but I think that seems to get rid of most of it, except for right there. But I can't do anything about that. The idea here now is if I want to insert 23, 23 has to be inserted at a particular spot. We can't just stick 23 anywhere. In fact, if I'm going to insert 23, I don't just want to stick it in the root. That displaces 8. And then what do we do with 8? So instead, I'm going to say, I'm not going to mess with any of the existing structure of the tree. What I'm going to do is find an appropriate place for 23 somewhere in the tree that doesn't displace any existing nodes. And the only places for that are the null pointers. If I'm not going to write over any of these values, then I'm going to be creating a new node pointed to by a null pointer. So what I'm going to be really saying here is, I want to insert 23, and I don't want to insert it where 8 is, because 8's there already. So I don't want to insert it in the left subtree of 8, because 23 is not less than 8, 23 is greater. So I should insert it in the right subtree of 8. That is, how whatever path we followed when we're looking for 23, we now need to put 23 into a similar spot, so that if I look for 23 again, I will find it. And the path I followed was from 8 to 20 to 28 to 24. That's the path I followed looking for 23. It suggests that I should put 23 at the end of that path, so that the next time I go looking for 23, I will indeed find it because it's here. That is, 23 is greater than 8, greater than 20, less than 28, less than 24, and so this null pointer should be where I insert 23. It was formerly a null pointer. Forget that. It's now going to be pointing to 23. It used to be a null pointer. Now it points to 23. And that means then when I follow that same search path I followed last time, which was this. This is sort of messed up here. But I said 23 is greater than 8, 23 is less or greater than 20, 23 is less than 28, 23 is less than 24. Oh, there's 23. That is, the insert procedure assumes your search is unsuccessful and says, do an unsuccessful search. And again, if you're going to insert duplicates, you could worry, otherwise about how you handle that, but it's just a small tweak of the basic idea. We're saying, let's do the unsuccessful search to get down to that null pointer where we would expect to find 23, and then put 23 there. So that the next time we do the search, it'll be successful instead of hitting a null pointer. And that's the basic idea behind insert. The idea behind insert is that we're going to search down the tree the same way we would do for find, which means the code will be very similar. We'll have those recursive calls to the left subtree, the recursive calls to the right subtree. We'll basically do a search down the tree until we find the right spot to put 23 in, and then we'll put it there. And the spot we put 23 in is where we would have found it to begin with if we had done a find. Notice this means that insertion is always as a leaf. Binary search trees build downward. Whatever value we insert is always inserted as a leaf. No parent or no children. Not necessarily inserted on a leaf. So for example, if I wanted to insert 19, 19 is greater than 8, 19 is less than 20, 19 is greater than 18, and therefore this is the null pointer I hit when looking for 19. If I do a find on this tree looking for 19, I don't find it. But if I do a insert, then that would be where I would go, and that pointer to null would become a pointer to 19. So that's the insert algorithm. How do we code that? Well, we follow the same 4 steps, the same 4 cases that we need to worry about. Namely, is your pointer null? If not, there we have the cases of equal to what's in the node, less than what's in the node, and greater than what's in the node. And so let's go ahead and write the function header, the method or function signature. And we have a tree node pointer tn and an e-type key. Now that is not going to be quite correct. Don't worry about that now. We'll come back to it in a moment. But that's not quite correct. And we will fix that very shortly. The rest of it's cool, though. It's for the most part correct, but some vital piece we're going to fix in a moment. So the idea here now is we can say, well, certainly if Tn is equal to null, then in that case, we have found a null pointer. That's where we want to insert things. So I say, well, Tn is going to be equal to a new tree node, and that could contain the key. So if your pointer is to null as the 24 left pointer was to 23, or 18's right pointer was to the null that should be pointing to 19, then that null pointer is where we insert a new value. Let's do the left next. Else if, let me put it this way. Else if key is less than Tn arrow left, or we could have said if Tn left is greater than key, but this way I think it's a little more clear. Then I can simply say I will insert the root of the subtree I'm worried about is Tn left, and then key is the value. I don't need to worry about returning anything because it's return type void. So I just call insert. Insert does its job, and that's the end of things. We're cleaving off the semicolons there accidentally. So there we go. So we have here if Tn is null, then create a new node. Otherwise, if your key is less than, this should be element. Sorry, folks. It was correct in your slide, but not on mine. So if key is less than the element inside that node, then you say, well, then I want to move to the left. So the left pointer of that node should be the root of the new subtree, and that's the same idea here. If I'm trying to insert, say, 23, well, or if I'm trying to insert, say, 2, well, 2 is less than 8, so that means I should call insert on this pointer from 8 to 3, and then this subtree will be the new subtree I insert into. Then we can say otherwise, if key is greater than Tn element, if key is greater than what's in your node, then you call insert tn right. So it's the right pointer that you want to have passed as your value, and then key. And then step 4, or case 4, we still need to worry about what if the value that you're trying to insert is equal to a value in the node. Then there's your duplicate situation. And you can choose to insert duplicates in the left subtree or the right subtree, which would put a less than or equal to under one of those. Or you can do what we're going to do, which is to say the sort of catch-all case does nothing. So I'm going to comment this out. There's no need for an else case. Don't even bother. If it hits the else case, nothing gets done. Whoops. If it hits the else case, nothing gets done, and that's exactly what we want. So we say ignore the insertion entirely and return if you find it that you're inserting something that's already there. Which would mean, for example, if I'm trying to insert 28, I say 28 is greater than 8, so call insert on this pointer to 20. Now we say, this being tn, 28 is greater than 20, so call insert on this pointer. And now in our third recursive call, 28 is equal to 28, so forget it, just return. And that's what happens here because we've said else do nothing, or we've commented it out entirely. So if these three are all false, nothing happens. That's the idea behind the insert. The recursive call idea of go to the left or go to the right using recursive calls is exactly the same as find. The only difference is instead of returning 1 or 0, we simply are trying to find that null pointer so we can insert there and actually have tn point to something. Now, interestingly enough, that's not quite right, as I mentioned before. The reason is that, remember, these are recursive calls. So when I am trying to actually insert something, say 19, for example, I have this tree, and I say, well, my first recursive call, this is the tn of my first recursive call. And I say, well, tn element is less than key, so I move down here. And I say this pointer is what I pass in along with my key. Say 19, I'm inserting 19. So I say, well, then that means I passed by value. That's tn2. Tn is greater than my key, so I pick that pointer to pass in by value, and also the key 19. So therefore, here's tn3. Remember, 18's right pointer is null. Here's tn3, and 18's less than 19. So this, let me make this a little bigger. This pointer to null is what I pass in, and so here's tn4. And I say, aha, now tn is null. That's exactly what I wanted. Because this was null, I can say, okay, tn equals a new node containing 19. And note what happens. We return from the fourth recursive call. The fourth tn goes away, and 18's right pointer is still null. That is, we have not changed 18's right pointer. Tn was a local copy. We passed the pointer by value. And so we didn't actually read the pointer. We made a local copy of that same address and looked at that pointer, which is fine when we're searching, when we did a find. This is how things work, but it's no big deal. We're reading the value. But when we want to change it, we don't want to be changing a local copy of the address. We want to be changing the real storage of the address. And what that means is I want to be changing this node. I want 18's right pointer to be pointing to 19, not some local copy. So what I really want was for, when I said this null pointer, I wanted tn to be a different name. We had 18's left, or 18's right pointer pointed to null. Tn is a renaming of that same cell, so when I say tn equals new node, 18's right pointer is also being assigned a new node because tn and 18's right pointer are the same node, the same pointer. So what I really want, one small change I want to make is I say, when you pass in a pointer, whether it be root or anything else, you want to pass this in by reference. And so here we run into that syntax I warned you about way, way, way back in lecture 2, where I said you might end up seeing something odd like pointer followed by ampersand. Do not get confused when you see that code. What that means, what that code means is it's a reference to a tree node pointer. Remember, the asterisk inside a function header does not mean dereference. It means that you have a pointer type rather than a regular type. The ampersand, likewise, in a function header does not mean address of, it means reference variable. We talked about that in lecture 4. So what this is, it's a reference to a tree node pointer. Tn will be a reference variable to a tree node pointer, a renaming of an existing tree node pointer rather than a copy of a tree node pointer. It does not mean we're doing dereferencing and then taking the address of, as in regular code. We talked about that, those two being inverses, that if I had n and I said take the address of n and then dereference that, you end up with n again. That's not what's happening here. These are not two inverse operations because they both have an entirely different meaning in the function header than they do in the rest of the code. So we're not saying take a tree node, dereference it, and then take the address of. We're saying take a tree node, what we really have is a pointer to it, and what we really have is a reference to that pointer. That's what that syntax means when you see an asterisk followed by an ampersand in the function header. It means you have a pointer type that you have a reference variable to. And so that's easiest to see, I think, if you come back to the original picture. And you say, well, what, actually, forget the original picture. Just say, what happens if I'm inserting into an empty tree? I can say, well, I have root to null. Now, when I make my first recursive call, if Tn is a completely different pointer, then when I say Tn equals new node, let's say I'm inserting 8, that's what happens, and root's still null. Where on the other hand, if I say, here's root is a name of that pointer, and if Tn is another name of that pointer, then when I say Tn equals new node, I'm saying Tn doesn't point to null anymore, it points to 8. So that's the difference. If Tn and root are the name of the same pointer, then when I change Tn, I'm changing root. If on the other hand, root and Tn are different names of different, we just simply say root holds null and Tn holds null. They're two pointers that both hold null. When I change Tn, I don't change root. Where here they're renaming the exact same cell as opposed to different cells. They would hold the same address in either case. They both hold null, they both hold null. But here we have two different memory locations with two different names holding null. Here I have the same memory location with two different names holding null. So that's why we need to pass by reference. And it'll be the same thing for remove. We'll need to pass by reference to remove as well. And the question is then, well, how do we remove? And the answer is we have 3 different cases involved with remove. The first 2 are relatively straightforward. If I want to remove a node, there's 3 cases. And the 3 cases correspond to whether you have 0, 1, or 2 children off this node. So we have here the 0 child case. If I want to delete 24. Well, just as with find and insert, I need to search down the tree and find it. So remove involves searching for the node first. When I call remove on 24, I say 24 is greater than 8, it's greater than 20, it's less than 28. Ah, there's 24. So we will search down it, and therefore we'll have that same recursive structure we had before. Now that I've got a pointer to 24, which will pass by reference, which we want to make sure we do because, for example, if I get rid of 24, but really what I'm going to want to do is delete your node, and your pointer will be equal to null. So what I want is to get rid of 24 and then set this pointer to null. 28's left child should now be null. If, on the other hand, I had this situation, and I said I have a local copy of the address, delete 24, set the local copy to null, now it's even more dangerous than insert. At the very least, if insert wasn't made reference variable, nothing would really insert. We'd allocate these new nodes, they'd be memory leaks, but the original tree would still work okay. Here it's very dangerous because if Tn and 28's left child are both pointers to the same node, then what happens here is when I say call delete on Tn, which is what we're going to do, that gets rid of the node just like we want it to, but then when I say Tn equals null, the local copy stores null. 28 still holds the original address of where 24 used to be, and so now 28 is pointing to freed memory. And that's very, very dangerous, as we've talked about before. 28 should either hold a legitimate address or null. And so if you pass this pointer by reference, then indeed when I say Tn equals null, as we're going to do inside our code, we're going to say Tn equals null. What happens is, well, Tn's a different name for this pointer, so this pointer will equal null. And that's what we want. So we need to pass by reference, just as with insert, so that this pointer is being set, not a different pointer that happens to hold the same memory address that that first pointer did. That's zero child case. You simply say, well, given a pointer to the node we want to remove, if that node has no children, just get rid of it, and then set the pointer to null. Let's say we want to get rid of 18. This is the one-child case. The one-child case is a little bit more interesting. We say, given a pointer to the node we want to remove, if that node has one child, well, consider what happens here then. Certainly in any case, if, say, this is the left child of 20, no matter what I have in terms of children of 18, by virtue of being off this pointer, it's less than 20. This is the left subtree of 20, 18, 14, anything else there. Anything pointed to directly or further down from this pointer is in the left child of 20. It's definitely going to be less than 20. So I could point to 14 just as easily as 18. Everything still follows the rules. Likewise, from here, everything here is in the right child of 3. Let me move this over a bit. Everything pointed to by this pointer, whether directly or further down, is in the right child, is the right subtree of 3, and therefore is greater than 3. Whether I point to 5 or 4 shouldn't matter. They're going to both be following the legal rules as far as they're both greater than 3. So in this case, I can just point around 18 to this node, or here I could say, well, forget 5, point here. In other words, 20 can point to 14, 3 can point to 4. It's not a problem because whatever the one child is of 18, that's definitely less than 20 as well. And whatever the one child is of 3 or of 5, that's definitely greater than 3 as well. So I'll always be able to, assuming there's only one child, whether it's the left or right child of 18, if our node is the left child of its parent, then its left or right child will be less than its parent as well. So call this temp. If temp is its parent's left child, then any children of temp, the left or right child, are also going to be less than temp's parent, less than 20 in this case. If temp is the right child of its parent, then any children temp has will also be greater than temp's parent. That means temp's parent can point to temp's one child without any problem. So I have to say, temp equals node, and then we can say something like tn equals, or pointer, I should say, pointer equals node's child, and then delete temp. So if this is our pointer, we say point a temp to, let me make this pointer. Point temp to your, this is PTR, point temp to whatever your pointer points to, then your pointer equals temp, the node's child, and then delete temp. And now 20 points to 14. Same thing here, temp points to 5, if this is pointer equals temp's child, and then delete temp. The one-child case is pretty straightforward too. The two-child case is a little bit more interesting and a little bit harder because we say, how on earth do we deal with this situation? And we say, well, let's say I want to delete the root, 8. If I get rid of 8, if I physically delete that node, that separates things into two subtrees, which are now not connected anymore because 8 isn't connecting them. And that's a problem. And you could come up with a number of ways of merging these. Trying to merge the left and right subtree somehow. Everything's going to be really nasty. Even if you just sort of plunk this right subtree as the rightmost element of the left subtree, that doubles the height of the tree. And since a lot of our operations will be based on the height of the tree, simply attaching the right subtree as the rightmost element of the left subtree is going to pretty much double the height of the tree in many cases. So we don't want to start trying to merge subtrees with the loss of 8. There's a number of things you might try out, but ultimately the way to solve this problem is to think back to insert before and remove. And to say, in those cases we were able to remove a value without really doing the structural modifications we thought we had to make. We didn't really need to delete that node or insert before that node. We could use little tricks and say, let's just manipulate our values and we're okay. And the same thing will be the case here. Ultimately, any sort of scheme you use to try and merge the left and right subtree somehow is either going to cost us on the short term or long term or both. What would be much, much nicer would be to say, let's keep this tree structure how it is. 8, the node containing 8 is too important to this tree. It's holding the other two halves together. I don't want to get rid of that node. What I want to do is get rid of the value. So instead of deleting this node, what I will do is just get rid of the value, 8, and I'll replace it with something else. Specifically, what I'll replace it with is the in-order successor. And if you just read that expression, that should be clear. What it means is the in-order successor. What the in-order successor is it's the what would succeed that value in an in-order traversal. And so since it's what succeeds the value in an in-order traversal, we could, of course, use the in-order traversal to find this value. Or what we could do instead is, instead of using an in-order traversal to find the value, simply recognize the in-order traversal of a node is going to be in its right subtree, or the in-order successor of a node will be in its right subtree. So what I have here is I say this node 8 has a right subtree. We know it has a right subtree because if it didn't have a right subtree, we wouldn't have 2 children on 8 to begin with. So since 8 does have 2 children, one of them has to be a right child, and so we know 8 has a subtree. And what I want to do is find the leftmost, or in other words, the minimum element in the right subtree. The leftmost element in the right subtree is going to be the in-order successor, because if you're going to picture doing in-order traversal on this tree, the smallest element in the right subtree is going to be the very leftmost one. That'll be the first one you hit with an in-order traversal, because you'll keep saying, well, first do the recursive call on the left subtree before you print the element. And so you'll say, well, before I print 20, do the recursive call on the left subtree. Oh, before I print 18, do the recursive call on the left subtree. So ultimately, you end up with hitting 14 before hitting anything else, and that would then, of course, even if you look at things in numerical order, be what comes right after 8. So the in-order successor of the rule is just follow the right pointer and then follow the left pointer until you hit a null, and the node right before that null is your in-order successor. And that's what you want, because I can say, I know for sure, because that's the in-order successor, I know it doesn't have a left child. If it had a left child, that would be less than 14, but still greater than 8 because it's in the right subtree. And therefore, since it's less than 14 but still greater than 8, it would be the in-order successor. So I know the in-order successor by virtue of being the leftmost or the minimum element in the right subtree, therefore cannot possibly have a left child. Now it might have a right child, but at most it's a one-child case. So I don't need to worry about endless recursion of the 2-child case. I simply say, for a 2-child case, I'll find the in-order successor, write it up there, write it over what's in the node I'm worried about, and then I can come down here and delete the in-order successor. In this case, it's a one-child. If it's a one-child, I simply point to that child. If it's no child, I simply delete that, and then this would be null. And since 14 didn't have any children in our original picture, 18's left pointer points to null rather than pointing to 14's child, because 14 didn't have a child. But the point is that would either be a 0 or 1-child case, and therefore easier to handle than our 2-child case. So that's how we'll do our 2-child delete. Any node that has 2 children, you don't delete the node, you simply find the leftmost element of that node's right subtree, write that over your value, and delete that. So if here I'm deleting 28, I say, well, there's 2 children. The in-order successor is 32. Write 32 over 28, and then get rid of 32, which is a one-child, or is a no-child delete again. So that said, the question is, well, can you use the predecessor as well? What about if I wanted to replace 8 with 5 instead of 14, or 28 with 24 instead of 32? Or if I'm deleting 20, I could replace it with 24. What about 18? And the answer is yes, you could do that. In-order predecessor, which is the maximum or rightmost element in the left subtree, would work as well. For this class, the standard answer will be in-order successor. You should use that on all the exams and everything like that. Technically, you could use the in-order predecessor as well, or you could flip and flop between them using some randomization algorithm or whatever you wanted to do. But since we want to have one standard answer, we're going to say use the in-order successor for everything in this class. But I'm simply pointing out that yes, the in-order predecessor could be used as well. The ultimate idea then is that the element sequence is maintained. I still have everything less than 14 and then 14 here. And since 14 was the minimum in the right subtree, everything remaining in the right subtree is still, everything remaining in the right subtree continues to be greater than 14. And so that's why we pick the minimum, so that everything that's left is going to be greater than 14 and the rule remains. Or if you pick the in-order predecessor, such as 5 for 8, everything, since 5 is the maximum in the left subtree, everything sitting inside the left subtree that's not 5 was less than 5. So if I write 5 up here, everything's still okay. So that's the idea here of why we would pick the in-order successor or the in-order predecessor. That way that everything that's left in that subtree, the rule is it maintains. Or the idea is if I write everything out in lexicographic order, here numerical order, 1, 3, 4, 5, 8, 14, 18, 20, 24, 28, 32. If I want to get rid of 8, then 5 or 14 should replace it. Those are the ones right next to it. That maintains the numerical order of the sequence, because the in-order traversal should always print out everything in numerical order. That said, all we really need to do here for the code, I'm not even going to necessarily bother putting this up against the tree picture. We simply say, well, here's the remove code. And I say we have a tree node pointer. It's a reference variable, tn, and I have an e-type key. And I say here, well, if tn is equal to null, then you simply return. There's nothing to do because you've now basically done an unsuccessful search. As you've searched for your value, you've hit a null pointer, which means it's not there. There's nothing to remove. Otherwise, we can say if key is less than tn arrow element, then you call remove on the left subtree, much like with insert. Otherwise, if tn is greater than, or a key is greater than tn element, then you call remove on tn right with a key. And otherwise, the only other possibility is that key is equal to tn element. And that means we found the value we want to remove, and then we put our cases here. And I'll leave that as an exercise for the, as they put it, the exercise for the reader. But the case is to handle, the code to handle your 3 cases is what you want now in this position. To say, well, now you say, if, tn left is null and tn right is null, that means it's a zero-child case, so then you just say, well, delete tn and have tn equal to null. Otherwise, if, and you basically have a conditional inside this else case that figures out whether you have 0 or 1 or 2 children and does the necessary code for that. So I'll leave that for you to play around with a bit, and we'll have answers up in the notes packet that you can take a look at. But that's the remove code. So that's binary search trees, and the big strength of binary search trees is to notice here that in general we will have, if we have a balanced tree, which means it's sort of a vague term, but it means roughly same number of nodes in both left and right subtrees, then that's going to be very useful from the standpoint of searching or removing or anything. The reason being that all our operations, find and insert and remove, can be thought of as being on the order of the height, h, where h equals the height. Because the worst case height would be our worst case time. Find searches from the root down to the node or your null pointer. Insert searches from the root down to a null pointer to be able to insert. And remove will search from the root down to it either finds your value at a certain node or hits a null pointer. And so all of those algorithms follow one path down the tree from root down to where your node or a null pointer and then stop. And so the larger height your tree has, the larger that path can be that you follow down to a null pointer in the worst case. But certainly, I mean, if you only have n nodes in the tree, you can't have a 18n height, because there's only n nodes to begin with. And the height, so the height's going to be n or less. If you have a balanced tree, it is log n. And if you're not familiar with that terminology, Lg equals log base 2. In other words, what happens is every time you make one of these decisions, you eliminate half the nodes in the balanced tree. You say, well, I've got roughly the same amount of nodes here, so by knowing that my key is greater, if this holds x, if key is greater than x, I know none of these nodes can be where key is stored, so I've eliminated half my nodes with one comparison. And if you eliminate half your nodes with one comparison, then every comparison eliminates another half of the nodes, and so on and so forth, or half the remaining nodes. You're basically trimming your value in half each time until you finally are centered on one node. That's logarithmic. I'm not going to prove this any more than that, but it's, like I said, it's in the book, I believe, if you want to see it in the book. The point is that in a roughly balanced tree, and we'll talk more about balancing later on, but in a tree that's roughly balanced, then you basically have a height of log n. That's an average case tree. So in the average case, be balanced, and so your three operations are going to be order log n. That is, if you have n nodes in your tree, the height of the tree will be logarithmic. The average binary search tree, the height is logarithmic, and so in the average case, the operations on your tree will run in logarithmic time, log of n. So there is your, if you have a million element tree, the log base 2 of 1 million is about 20. So if you have a million element tree and it's basically balanced, about 20 comparisons would bring you from the root down to the deepest leaf. And so the operations couldn't require any more than 20 comparisons. The first comparison would get rid of 500,000 of your nodes. You have 500,000 left. The next comparison would get rid of another 250,000, leaving you with about 250,000. And every successive comparison would kill half of what you remain, because you either would look in the left subtree or the right subtree, but not both. And so with every comparison, you kill half of what remains. What you're left with then after log n comparisons is just the one node. In the worst case, is as unbalanced as possible. You have your nodes in one linear chain. You have, for example, all right subtrees. There's never any left subtree. You have, for example, 1, 2, 3, 4, 5, 6. A whole chain of nodes that is just every deeper node is greater than the next one. You could have a binary search tree arranged that way, like I said. You could have 1, 2, 3, 4. There's an example of a binary search tree where everything's in a line, and you can imagine the numbers 1 through n chained like that. Clearly, the height there is on the order of n. And so there, the worst case for these operations is, for all three of them, is linear time. If your binary search tree is arranged in that fashion, you have a linear operation because the height would be linear, and therefore an operation depending on the height is linear. If the tree is balanced, the height is logarithmic, and so the operations, which all depend on the height, would be logarithmic. So what we'll look at for the next 3 lectures, which won't be part of the exam, but the next 3 lectures involve what is known as an AVL tree, where what we say is, let's try to enforce the tree being balanced. If we can ensure that the tree is balanced, then we can ensure that the tree has logarithmic height, and that would ensure that our operations are always log n, as opposed to being log n only in the average case. We will talk about that next time. Till then, that's it. Take care. See you then.